Welcome to a very science nerdy edition of Mondays with Mike. Now, this Monday here, we're going to be talking about and delving deep into something called the Coriolis Force or the Coriolis effect. Now, why did I decide to talk about this instead of football, which, I like talking about every Monday? Well, it had to do with an Instagram post and an Instagram argument in the comments that I came across a couple of days ago. So what happened was, and I'll put a video up here for you to take a look at. So this demonstration was posted to an Instagram. I'm showing you the same video on YouTube, but this actually came from Harvard. And it was some physicists there just doing a basic sort of demonstration of the effect that we see on a spinning Earth. And they're exaggerating the effect here by spinning really fast and then trying to throw a ball at each other and showing that the ball goes off to the side. Kind of like air kind of moves off to the side when, hurricanes form and we see areas of high and low pressure. Well, what looked to me to be a really neat demonstration apparently caused some controversy in the comments, which how social media is. I mean, you could put a picture of a kitten and there's going to be some people arguing in the comments about something, right? So in this case, there were several people who commented that this is BS and, well, I'll read you some of the comments, but let's start out with what the Coriolis Force is. First of all, why is it called the Coriolis Force? Well, because it's named after the mathematician who first described it, and he was a Frenchman, and his name was Gaspard Gustave de Coriolis. I looked up how to pronounce it, by the way. So this was back in the 1830s. Now, in the 1800s, there was a lot of extremely important math and physics and discoveries that were taking place with regards to things like electricity and magnets and spinning objects and energy, because they're working on steam engines and things like that. There was a lot of really, really important stuff that was happening. Not so much meteorology specifically. And in fact, it's interesting that when this scientist Coriolis, when he first described this effect, he was studying spinning objects, and he came up with a mathematical way, probably way over my head, to describe how the energy transfer of things if you moved across a spinning object or body. And so, and we'll talk about that a little bit more coming up and the effect that it has on the Earth. But the bottom line is, the effect actually was not used in meteorology until really the 20th century, until the early part of the 1900s, I believe, was it really applied to the atmosphere. Maybe even later than that, because before that, this Coriolis effect was really used in physics and mathematics, not as much in meteorology itself. So, it goes back 200 years, but really has only entered the discussion in weather for maybe the last 70-ish, maybe 80 years. So what causes the Coriolis effect on Earth? Well, the simple way to put it is the Earth spins. So we're on this big rock that is just about a sphere. It's people say, well, it's not really a sphere. It's basically, for all intents and purposes, we're on a sphere, and it spins around once per day, technically every 23 hours and 56 minutes. And because of that rotation, when you have wind, or really any object, water too, that's moving along the Earth long distances, especially at faster speeds, there's an effect that takes place that diverts it off to the right in the northern hemisphere and to the left in the southern hemisphere. And it can be described a couple of different ways. The really fancy way to think about it is called conservation of angular momentum, which some of you may love. Some of you might not want to hear about anything like that because brings back bad memories of like high school earth science class. But it's just to say that when you watch a figure skater And you know they always do that super fast spin at the end of their routine, right? Well, when they start with their arms out, and they have a certain rate of spinning, and they're spinning kind of fast, but not that fast, right? Then when they pull their arms in, they get a whole lot faster, and that's how they maximize that spin. And then they're spinning so fast you can't even believe that they're doing it. But that's called conservation of angular momentum. When you have this wider reach of like the mass of your arms, they're out here, then you spin at a certain speed. And once you make it shorter and shorter and you move it in, then it spins faster and faster. And so that happens with things like tornadoes. You know, you have this wide, you know, circulation, and once it gets going in the middle and compresses into a smaller, you know, cone or rope, then it gets a whole lot faster, right? So we kind of know that. And we kind of know, even like little kids can do this, where if you have your arms out and you jump up in the air and spin, if you pull your arms in while you're in the air, you spin faster. So I think a lot of people, like, you know this happens. You might not think about why it happens, but it definitely does happen. So anyway, that's the conservation of angular momentum. So if you have air that's, let's say, at the equator, and then it's on the widest part of the Earth, okay, the widest part of the sphere. Now, when it moves up, let's say it moves up to Texas, well, we're actually moving up in latitude, so the sphere is smaller, right? When you go all the way up to the top, you're not moving at all. You're just spinning around at the North Pole. So you go from here to here, and that's just like the figure skater pulling his or her arms in. And so the air speeds up, and as it speeds up, it moves to the right because it wants to go faster than the surface of the Earth. So that's what we call the Coriolis force. Now, what's interesting is that, and the reason that I wanted to do this is that in this demonstration, there were a lot of comments, very strong, condescending comments, like this. So let's see, Caedmon, who has this as his, that's him. Kind of a nice little drawing. He says, this literally isn't true and doesn't happen, LMAO. That's laugh my blank off. No long-range sniper in the history of ever has calculated for the Coriolis effect. Well, I will give you that. I don't think that snipers calculate for the Coriolis effect, although they do have to account for wind, right? And the wind is in part driven by the Coriolis effect, but let's just take the wind away from it. Let's talk about the sniper, because some of you out there might be agreeing with him. Well, if the Coriolis effect is true, why doesn't a sniper have to move his, the point of his, rifle a little bit? Well, because we're talking about a tiny effect over a very short amount of time. So when you're talking about the Coriolis effect, the Earth spins around once per day, one time per day, which means every second, okay, get this, every second it spins around 0.0001 times. So that's your rate per second. It's extremely slow. So it's only going to affect things that are at a very large scale, like many miles, tens of miles, hundreds of miles. That's where the effect is really going to be noticed. If a sniper shoots a bullet and the bullet is in the air for a fraction of a second, no, it is not going to really be affected by the Coriolis force because the Earth only moved 0.0001 rotations in that split second that the bullet was in the air. So that's the explanation for that. Somebody else brought up, like, well, what about like cannonballs or, like these big mortars or whatever that launch really far? Are they affected by the Coriolis force? Yeah, I mean, believe it or not, they are. It's probably not a big noticeable effect, but the longer you shoot something and, the farther it goes, and especially the more change in latitude there is, then yeah, it will be affected by the Coriolis force. Okay, Michael Parton said, whoops, I dropped my glasses. Michael Parton said, Why doesn't this happen to airplanes or helicopters? Why doesn't this happen to balloons? Well, let's talk about airplanes and helicopters. Helicopters don't fly that fast. Remember the TV show Airwolf? Remember that with Jan Michael Vincent? That helicopter flew pretty fast, I think. Most helicopters do not fly that fast. They're limited as to how fast they could fly because the thing has to rotate, the rotors have to rotate, and you can't break the sound barrier, so you can't go forward that fast because it creates all kind of instability. And I'm not a pilot, but I used to fly in the helicopter every day here with Fox 26, so I learned a little bit from the pilot, but there's a maximum speed that they can travel. So let's say and I don't know, maybe it's 100 miles per hour, maybe it's 150 miles per hour, I'm not exactly sure how fast, but suffice it to say, it's not moving that fast, and they're not traveling that far. So helicopters, is there an effect? Yeah. Are you gonna notice it? No, because it's probably like a couple of inches. It's not anything that you have to account for. Airline pilots will tell you, yes, there is an effect, but it's actually been measured and proven that it's not enough of an effect to change their route and their flight planning. The main thing that they have to worry about is, getting from point A to point B in the shortest distance, and so they follow the highest winds. So they have a tailwind to get from Houston to London. And so they want to follow that tailwind to save the most fuel and everything else. And they're navigating to the point that this Coriolis effect is literally going to be moving them a foot. I'm just throwing out numbers. Inches, maybe a foot, maybe it's 6 feet, over the course of their travel from Houston to London. And there's a way to calculate it. I could calculate it based on their speed, their ground speed. I didn't, but I imagine, let's just say it's several feet or several meters. It's not anything they need to account for, but it absolutely happens. Let's say J. Weston 24 said, this actually proves the Earth is not spinning, because if it were, we'd encounter similar results. And then he put 3 of those laughing emojis. Oh, so smug. It's like laughing with the tears coming out, the laughing, crying emojis, you know what I'm talking about? These, those, yeah. So how obnoxious. This actually proves the Earth is not spinning, because if it were, we'd encounter similar results, like we do. That's what we see every day. Like, we see hurricanes and tornadoes and tropical storms and cold fronts and all of this stuff that's absolutely, like, literally what you just said doesn't exist. And we see it all the time, every day. And it's really weird that that J. Weston 24 doesn't believe that and chose to put laughing emojis. Now, this one takes the cake. This one was my favorite, okay? This is from Johnny Rodriguez. And I know a Johnny Rodriguez, and this is not the Johnny Rodriguez that I know, because he wouldn't write something dumb like this. But anyway, so this is Johnny Rodriguez. He says, the Coriolis effect has been proven in many ways to be bull blank. He didn't list how many ways. He didn't list who proved it, disproved it. But he said the Coriolis effect has been disproven in many ways to be BS. If it was real, then when you rode in a hot air balloon, you'd be able to lift, hover for a while, then land in a completely different place. That's literally what hot air balloons do, right? They don't have an engine. They don't steer themselves. They go up, and then the wind blows them somewhere, and they end up in a completely different place. This is what happens on the internet, I swear to God. If it was real, then if you rode in a hot air balloon, you'd be able to lift, hover for a while, then land in a completely different place miles and miles away. Yeah. Yeah. Come on, Johnny Rodriguez. That's what hot air balloons do. Now, to his point, let's just say that we're in a different kind of situation and there's no air, and we're not talking about the wind blowing. Let's just say that the Earth had no atmosphere at all. Would there still be a Coriolis effect? Absolutely, 100% yes. It would involve any moving objects on the Earth. The farther they go and the faster they travel, the greater the effect will be. Now, in the effect of a hot air balloon, you have to think about this. The Earth is spinning, okay? All of us are spinning with the Earth. You, me, Denise Middleton's over there. Everybody is spinning with the Earth. So if you're on the equator, you're moving at 1,000 miles per hour. Doesn't feel like you're moving at 1,000 miles per hour, but you are, because the Earth has to spin around once every day, and the Earth is about 26,000 miles around, and so you've got to move 1,000 miles an hour. So anything that moves, anything that's on the Earth is already moving at 1,000 miles per hour. And so if you were in a hot air balloon and you took off, you would already be moving at 1,000 miles an hour. See, so as the Earth turned, you'd be sitting over the same spot. And there is no Coriolis force because you're not moving with respect to the Earth. So that's why, if the wind weren't blowing, yes, you would absolutely go up in a hot air balloon, Johnny Rodriguez, and you would be there, theoretically with no air, and then you would come back down in the same spot, yes, because you're moving at the same speed as the Earth. And incidentally, anybody who's interested in space and rockets and things like that, it's the exact same thing. That is why NASA, and that's why SpaceX, and all of these rocket companies, they launch, where do they launch? Florida. They launch from South Texas because that's closer to the equator, and they're moving faster with respect, they're moving faster with respect to space and to get into orbit. They don't launch from Canada. They don't launch from the South Pole. They launch from places in the southern United States because that area is actually moving faster. So there you go. So I don't mean to pick on this guy, Johnny Raw, and it's Raw, like R-A-W, Rodriguez. Don't mean to pick on you, man. I'm sure you're a good dude, but you're just, hopefully you're watching. So why is the Coriolis force important? Well, if we didn't have a rotating Earth, then we wouldn't have rotating storms. So we wouldn't have hurricanes, we wouldn't have tropical storms, we wouldn't have winter storms, we wouldn't get cold fronts and warm fronts. We wouldn't get anything that basically makes weather if this effect were not taking place. Now, you may hear two different terms. One is Coriolis force, and the other one is Coriolis effect. Why? What's the difference between a force and an effect? Well, it's based on how you look at it, where you are when you're looking at this. It's called a reference frame. And the perfect example that I can think of is when you are driving in your car. So let's say you're a passenger in the back seat of the car, right? And the driver takes a hard left turn. What do you feel in the car? You feel like you're being pushed against the door, right? You're like, whoa, slow down there, buddy, right? He turns the wheel hard, you get pushed against the window. Feels like a force being acted on you. So if you're in that car, you think that turning applies a force to you that shoves you against the door, kind of like gravity, right? Feels that way. If you're outside of the car, that's not what you observe. If you're outside of the car, you see the car and everything in it turning. And the only reason that this person in the back seat is pushed against the door is because the car is turning. The person is still going straight, because that's what everything does in nature, goes straight unless there's a force that pushes it. So the car turns, you keep going straight, and then the door pushes you to the left. So it's based on what you're looking at. So Coriolis force would be sort of what we observe here on the Earth. And like the Coriolis effect would be kind of what we notice if we're looking at satellite imagery or something like that. You're looking at it from the outside. So it's very, very important. And I know it's a bit of like a mind like game that you got to play with yourself. Like, just think about being in the car, or think about, oh my gosh, that ride, the Gravitron. You know the Gravitron, like at the rodeo. I've never gone on it. My daughters went on it, and it spins you around really fast and it creates this what's called a centrifugal force. Well, you feel a centrifugal force, which is you feel like you're being pushed to the outside of the Gravitron. It's pinning you up against the wall. But somebody from the outside sees what's called a centripetal acceleration, meaning that the thing is spinning around and it's just, the wall is keeping you from flying out. So the wall is applying a force to you to keep you spinning. So that kind of brings me to another point, which is if you doubt that the earth is round, which a lot of people do, and this is what's part of the comments. They say, well, the earth is flat, this is all a conspiracy. If you believe that the earth is flat and that the Coriolis Force is fake, all you have to do is look at other planets. The perfect example would be Jupiter. Now, Jupiter is the biggest planet in our solar system. It also rotates faster than the Earth. So the Earth takes 24 hours to rotate, minus a couple minutes. Jupiter takes, I think, about 10 hours to rotate. I have to look this up, but about 10 hours. So it's very large. It spins very fast. And so the Coriolis force is much, much stronger on Jupiter. So you get these gigantic storms. And there are these huge hurricane-like storms on Jupiter that spin for like hundreds of years. And that's absolutely a storm that's caused by this Coriolis effect. It's so we could see it on other planets. And any planet that's spinning that has an atmosphere will have a Coriolis effect. It also does govern oceans and ocean currents. We get a broad clockwise current in the Atlantic Ocean based on the fact, well, it's complicated, but you get the trade winds at the tropics that blow the water from east to west, and then you get like cold fronts in the top part of the ocean that blows it from west to east, and it creates this clockwise rotation to the ocean. And then, well, this is getting deep into the weeds, but it creates like a slightly higher level in the middle of the Atlantic Ocean. And when the water flows out, the Coriolis force turns it to the right, and you end up with like slightly warmer air, keeping the climate of like Ireland and the United Kingdom warmer than it otherwise would be. Like if you were to go to like Minnesota, which is I think about the same latitude as London, give or take, it gets like bitterly cold, 20, 30 below zero in Minnesota. And that never happens in London because they're surrounded by warmer ocean water that gets driven by that Coriolis force. Why do people debate science? That was the last thing I wanted to ask. And I'm not talking about, not talking about that. I'm talking about like completely settled science that's been around for like 200 years. And it isn't just science, it's math, really. I mean, to say that the Coriolis force doesn't exist is similar to saying 2 times 2 isn't 4. Or, 3 plus 3 isn't 6. It's all a conspiracy. It's very basic. It's very well understood and very basic. And there's no reason to pretend that there's some sort of weird, I don't know, if it's a conspiracy, who's driving the conspiracy? Why would we invent something for 200 years to pretend that hurricanes spin around and just to what, mess with some people on the internet? I don't know, man, it's weird. So I hope you learned a little bit of something about the Coriolis force. It's far more complicated than I described, because when you really get into atmospheric science, and maybe look, moms and dads, if you have kids, maybe teenagers that are really into weather and they want to be meteorologists, maybe you could show them this and they could, do some more research online about really what makes this tick, because there's a lot of like trigonometry involved, which everybody hates trigonometry, right? There's a lot of stuff that's going on with sines and cosines to calculate the Coriolis force, and velocities, and orbital velocity and things like that, angular velocity. So there's a lot of cool stuff here. I know this might have been boring for many of you. I hope you watched it all the way through. If you ever have any questions about this, you can message me. I mean, I'm available on Facebook, or my email address is mike.iskovitz@fox.com. Okay, mike.iskovitz@fox.com. And, if you want to send me a message, if you're curious about what in the world is, going on, I can maybe send you some resources. So anyway, shout out to my mom and Neil. Still thinking about our visit. We had a terrific visit. Oh, before I let you go, last night we saw Five Nights at Freddy's. I went with, because my teenagers had already seen it. So my one teenager stayed home, and I went to the movies with my 12-year-old and my other twin, almost 17-year-old. And it was good. I'm not going to say it was great. It wasn't what I thought it was going to be. It was sort of more, it was slower than I thought it was going to be. And it was like darker and sort of more, I thought it was going to be funnier. It really wasn't funny. So I was expecting the monsters to be like chasing the people around the whole time, and they didn't. So I was a little disappointed in that, but it was still good. It's still a good movie. So anyway, thanks for joining me for Mondays with Mike. If you found this informative, please hit the like button if you're watching on YouTube or on Facebook. Please share it with somebody who you think might like really nerdy earth science kind of stuff. And I hope you have a great week. By the way, stormy weather on the way late this week. So we will be watching that for you in the Fox Red Weather Center.